Hello and welcome. In this video, we are going to go over some psychrometric closed processes. Psychrometry is a science of or engineering of moist air, where dry air and water vapor are mixed together. We will go over how to find states of moist air using the MA model and talk about mass and energy equations for the closed process such as for simple heating, where you're heating a closed volume of moist air and there is no water involved. Simple cooling is the same thing, or cooling, but there's no condensation, or humidification and dehumidification, where water may condense out. But these are challenging problems because we are talking about a closed system. Okay, so let's go over a couple of animations to make sure we know psychrometric properties, etc. So this particular animation, 12A psychrometric chart, shows you different kind of moisture specific properties that are used in finding the state of moist air. In this slide, you can see that, for instance, using a psychrometric chart, to find a state, suppose relative humidity is given 60%, temperature is 40 degrees Celsius. So you have the temperature column, temperature axis, this is the temperature axis, and the humidity lines, relative humidity lines are here, 60%. That's how you pin down a state and find properties from all the other axes. So, but remember, this chart is based on a standard pressure 100 kPa. So if the total pressure changes, you need to look up a different chart. Fortunately, in test, we don't have to do that, and we'll solve a problem where the total pressure can change. So this is an example of, in this case, it's humidification. You can see the water is evaporating and how it affects the state is shown here. Or in this particular slide, we show dehumidification and also simple cooling. First part, as it goes from 1 to 2, you can see that it's cooling without any condensation, but from 2 to 3, we see condensation involved. Okay, so let's go and see if we can quickly set up a problem, go over the test step, and set up a problem and solve it. So obviously, just to find a state, we could go and use the MA model, but let's solve the problem a little more interesting. So we are after closed processes, so we'll follow the closed system specific branch, and you can see that HVAC psychrometry is right here. There are video problems here, solutions, and let's go launch the app. As you can see, it's a little more complicated. You can see the moist air is the default fluid here, and there are so many other properties. For instance, the pressure, there are 4 different pressures. This is the total pressure, pressure of dry air, pressure of water vapor, and this is the saturation pressure, the maximum water vapor pressure that there could be at a given temperature. Likewise, you will say there are different kind of mass of dry air, MA, MT is the total mass of vapor, mass mg means mass of saturated state, mass of vapor in a saturated state. Notice that if you select H2O, for instance, we may have a state where we are injecting water or water is condensing out. Then if you select H2O, the properties changes to our familiar PC model. So basically, the app, the state panel works with 2 different models superposed based on what fluid you choose. Obviously, the process panel is more complicated because it could be 2 different beginning state and 2 different final state. For instance, suppose you have a moist air and final state is moist air and condensed water. Or you can have moist air plus some water being sprayed, and there could be 2 different states here, and the final state could be a single state. So let's go and set up a problem very quickly. See, atmospheric pressure is the default pressure. So let's say we have a large tank, a 10 meter cube tank at, let's pick some arbitrary temperature, let's say at 30 degrees Celsius, and it has a 90% relative humidity. Well, the state is calculated. So how much vapor does it hold? Right here, mass of vapor. Of course, it is less than the saturation mass of water vapor. in the graphics panel, you can see the state on a psychrometric chart. So for state 2, let's say we are cooling it down at constant volume. We can do that also for constant pressure later on. If it's constant volume, we cannot say the total pressure is 100 kPa because we don't know. As we cool down, the total pressure in the tank may change. Okay, so volume is the same. What else remains same? Mass of dry air cannot change. And let's say we cool it down to temperature 10 degrees Celsius and we see water condensing out. So in that case, the relative humidity must be 100% because if water is condensing out, the air must be totally saturated. And that gives us the complete state. As you can see, the total pressure has gone down. And this will be almost impossible to do manually because total pressure is not the same. Okay, now let's go to state 3. Well, by the way, to confirm that water must have condensed out, see the mass of vapor is now 0.093 and in state 1 it was 0.273. So obviously the air is holding much less water vapor and some must condense out. So let's say state 3 is our water condensate. The condensate has assumed to always have the temperature of the final state, which is T2, 10 degrees Celsius. And by convention, we assume it's saturated liquid. It doesn't matter because enthalpy is so, it doesn't matter whether you put pressure to be 100 kPa or X to be 0, it will produce almost the same amount of enthalpy. Okay, in the process panel, we have a single beginning state. We leave this BB state alone because we have just moist air. And in the final state, we have state 2 is the moist air, and state 3 is our H2O, the condensate. So now that we have loaded the states, we know the work is 0 because it's constant volume process. There is nothing else going on, no electricity, no external. If you click the calculate, heat transfer is calculated. But remember, sometime if you don't see that, it's always a good idea to click the super calculate button to update all calculation. If you go to the state panel, you'll see that for state 3, the mass has been posted back. That is how much mass, how much condensate came out. Just suppose the problem was that instead of constant volume, it was constant pressure. Then what all that will change is that we will say pressure was the same. But in that case, the volume will change. So there will be some boundary work. So we cannot say W external equals 0. We have to write here is boundary work, which is P1 times P1 and P2 are the same. Volume at 2 minus volume at 1. That's the boundary work by definition. If I do a calculate, you'll see if I put the pointer over, it will find here I've calculated the boundary work, but Q is not found. Well, you click the super calculate button, it updates all the panels, and now Q is found. So you will see that even though the problem involves moisture and very advanced concept, the way we have solved it is just about the same as any other closed process problem, except in this case we have used two different models, MA model and PC model. To learn more about how to use psychrometric apps, in addition to the closed processes, also go over the psychrometric applications for open systems. That's also from chapter 12.